Thanks. Great to be here and give me a chance to tell you about my journey to try to understand the connection between sleep, dreams, and memory. And the journey begins here. And this is a rat brain. What you see here, rat brain with the overlying neocortex removed to reveal this structure, the hippocampus. Now, the hippocampus lies deep in the medial temporal lobes. If you take your fingers and you push them into your brain, that's where your hippocampus lives. And the hippocampus became the subject of great scrutiny in memory back in the 1950s when a patient named HM, now known as Henry Meliason, underwent a surgical procedure. It involved removing portions of the hippocampus in both sides of his brain to treat epilepsy. What was discovered after that surgery was surprising, and that is that HM lost the ability to form any new memories of his experience. His life literally ended that day on the operating table. And for the rest of his life, he never formed a new memory. Now we fast forward about 20 years to the early 1970s, and John O'Keefe, a researcher working in his laboratory at the University College London, made another discovery. By placing electrodes into the brains of rats and recording from the individual brain cells, this is a cross-section of the hippocampus, and you see an individual hippocampal neuron, and allowing a rat to simply explore on a little tabletop. What O'Keefe discovered was the individual cells would respond in different locations on that tabletop. Different cells would fire in different locations. There were certain places that they liked to respond to. He termed these cells place cells, and for this discovery, he was awarded the Nobel Prize in Physiology of Medicine in 2014. Now, what this suggested was that the hippocampus was actually forming maps of space, and that the same cells that were involved in forming these maps were involved in memory. Now, this is where I became interested as a young scientist in trying to understand mechanisms of memory. And I thought, if I could only record from enough neurons, I could get an image of a memory and figure out how it's made, where it goes. But now, just as understanding an image from a single pixel on a television screen would be difficult, you need a pattern. You need to see maybe 10, 50, 100. If you could see more pixels, you could identify more images. And so using the same strategy in the brain and using a technique involving placing an electrode into the brain and placing many of these electrodes in the brain and isolating the activity of individual neurons, I was able to record from patterns of neurons within the hippocampus. Now, I'm going to show you now what an actual experiment would look like. So I'm a young scientist. I'm in the lab. I've got these electrodes into a rat's brain. I'm looking at patterns of activity. And this is a rat running on a maze. What you see here are these little color-coded brain cells. These individual dots are action potentials. This is what brain cells use to communicate with one another. And what you see here is as the animal's moving, this light blue cell fires here, the dark blue cell fires here, different cells firing in different locations. This is the phenomenon of place cells that O'Keefe was given the Nobel Prize for. But there's another thing that you can notice, actually if we get the volume back up, and that is that you can hear when an animal is running, there's a rhythm. This kind of, can you hear that? This rhythm is engaged whenever an animal is attentive and moving in the world. When the animal stops, the rhythm goes away. When the animal moves, the rhythm comes back. And so with this is what the brain looks like when the animal's exploring space, forming memories of moving in space. But with this alone, we can't really tell what does a memory look like. We have to take an additional step. And I'm going to show you exactly the same data. This is the same experiment. Oops. Only now, instead of showing you those neurons firing, I'm decoding that activity. And that is, I'm saying, every instant, we ask which cells are firing, and then say, where would the animal have to be in order to see that pattern? And then indicate that location with a little triangle. Size of the triangle is our confidence. So what this is like is, suppose we're recording from the brain and the camera goes out. I can't see where the animal is going anymore, but I can still measure brain activity. I would be able to track where the animal is every fraction of a second. The brain is telling me where the animal is. So this is where I actually started. I'm studying memory. I can see these patterns. I can track animals on the maze. This is pretty cool. But this is where serendipity stepped in. I have to tell you a little story. So I'm running one of these experiments. Animals run on the track. I've recorded the data. I'm done with the experiment. I take the animal off. And I put it on a little platform and then turn around to start analyzing the data. I still have the audio monitor turned on. I'm listening to activity in the brain. And while I'm working, I hear in the background, I hear this. It's the sound that the brain makes when the animal's moving. I hear place cells firing, as though the animal is running. Well, I'm a little bit concerned. I think maybe the rat's making a break for it. I turn around, and fortunately, rat is not scurrying down, off toward the door. No, the animal's asleep. He's sound asleep. What I'm hearing is REM sleep, rapid eye movement sleep, or what you think of as dream sleep. The rat is dreaming. He's dreaming of running on this track. Well, I wasn't doing this experiment to study sleep and dreaming, but there clearly is something surprising here. So immediately I start going to look at this data during sleep. And what I find is, indeed, during sleep, immediately after running on one of these mazes, these patterns that you see here reappear. They're reactivated during sleep. And in REM sleep, indeed, the animal is running, the place cells are firing, the animal is dreaming about running on the track. So I immediately thought, I need to understand what's going on during sleep. But now REM sleep is not the only kind of sleep. In fact, most sleep is what we refer to as non-REM sleep. And in non-REM sleep, which there's a common misconception is not dream sleep. In fact, if you go to sleep right now, hopefully none of you are doing that, the first stage of sleep you will enter is a non-REM state. And in that non-REM state, if you nudge your partner, wake them up, and then ask them what they were dreaming about, what they'll report is they were dreaming, but these dreams were fragmented, they were kind of boring, they had mundane content, and they related to stuff that you were doing during the day. And that is, these are not the kind of dreams that you wake up, that you write into your dream journal, that you talk about at the breakfast table. I was riding an ostrich, in the Alps. Not those kinds of dreams. But it is the kind of dream state that we were able to analyze. So I thought, okay, we've seen that dreams are being replayed during REM, but what about in non-REM? And when we looked at that data, what we found was something surprising. And that is that, indeed, during non-REM sleep, memories are also being replayed. But as you can see here, in this inset, here is a rat. He's finished running on a maze. He's been taken off. He's sitting on a little platform. This is off to the side. And what you're seeing is the decoded activity of a brief fragment of their dreams. And what that dream looks like, you can see that little triangle. This is running at real time. As you see a short snippet, this is the animal very quickly, the hippocampus, the brain, is running through a little section of the maze. It's running through about 10 times as fast as the animal actually moved. And in this case, surprisingly, it's actually running backward in time. That's running backward in time. It turns out in this non-REM state, memories are replayed. They're fragmented, they're compressed in time, and they can go forward or backward in time. Well, this is surprising. And we thought, is this the only time that this kind of dream and memory activity occurs? But we also realized that non-REM sleep actually looks a lot like another state where perhaps you're not fully paying attention, and that is just the quiet, wakeful state. If you're just sitting and you're thinking, or maybe daydreaming. Now, rats do this too, and we can look to see what is the hippocampus doing when rats just stop and think. And that activity looks something like this. So this is another slide where we're looking at a little fragment. It's about half a second of activity. And And I've slowed it down for you this time. And what you see here, the little light blue path is designed to help you see where that memory trajectory is going. What you see is it starts where the animal is sitting right here, and it runs about 5 meters along the track. This is the same data that you were seeing before, except now, rather than tracking where the animal is stopped. And at that moment when it stopped, its hippocampus continued to run forward along the path. But there's another property of this reactivated memory that was very striking, and that is what looks like a continuous long trajectory is actually broken up into small pieces. And that is that these memories are actually made of smaller fragments that are put together, assembled in a way to give you what appears to be a continuous path, the animal thinking about where it will go. Now, so now we have dream sleep, rats running through their dreams, non-REM, they're reactivating small fragments, maybe forward and backward in time. Now in quiet wakefulness, they're able to think forward by putting together little pieces of memory. But how would you distinguish a real dream? I say, oh, the rat's dreaming. But you say, are they really dreaming? And this is just some patterns in the hippocampus. Your dreams have something which really distinguish them, and that is you can report what you're experiencing. You see things. There's imagery that's associated with your dreams. Well, I could do the same thing with rats and wake them up and ask them, what were you dreaming about? They probably wouldn't answer. Actually, they don't answer. I've tried it. But what we can do is we can record directly in their visual cortex, their sensory systems that carry out perception itself. So we did this experiment where we recorded in the hippocampus and in the visual cortex. The animal went to sleep. And in non-REM sleep, what we found was when the hippocampus runs through a sequence, this compressed sequence along a maze, the visual cortex also responds with a sequence corresponding to the imagery that it saw. The rats see what they're dreaming. But there was an interesting structure to this visual cortical memory interaction, and that is activity in the visual cortex started just a little bit earlier than the hippocampal memory sequence, suggesting that during sleep and in this non-REM state, the visual cortex started out a little dialogue with the hippocampus. It said something like, you remember that little polka dot pattern? Visual cortex's polka dot pattern. Sends it to the hippocampus. The hippocampus says, yeah, that polka dot pattern, I remember where that was, and this is what I was doing when that occurred. Visual cortex cues the hippocampus. Hippocampus replays a sequence of memory or the experience that occurred associated with that pattern. And then that sequence is played back to the visual cortex to recreate the imagery that was associated with it. This is how dream perception occurs. Now, if that is the case, if indeed the visual cortex can cue memories, perhaps you can cue the visual cortex, and that is if you could influence what was going on in the sensory cortex during sleep, maybe you could cue particular memories. And Ken Paler, a colleague of mine at Northwestern University, did an interesting experiment to test this idea that perhaps you could influence memory processing during sleep. And the task was this. It's a little game. You're probably familiar with it. It's just matching cards. So you lay out a little array of cards, and each card has an image associated with it. Picture of a cat, picture of a teapot. And what you have to do is you have to remember, flip over the cat. Where is the other cat? You flip over, you have to remember the location of cards. But what Ken did was a little bit different. Same matching game, except that whenever you flipped over a picture, he would play a sound associated with it. Flip over a cat, you hear meow. Flip over a teapot, you hear psst, teapot whistle. So you learn the association between images, their location, and a sound. And then when people would go to sleep, in non-REM sleep, he would play one of the sounds. He would just play the cat. So while you're asleep, you're hearing meow, meow. And what was surprising was when people would wake up and they'd go to solve this matching game, they would be better at the cat than they were at the teapot. He was able to selectively cue and enhance memory for specific items by simply cueing it during sleep. And we thought, oh, wow, that's cool. Can we do this in a rat? So we did basically the same experiment. So we have a rat, it's in a maze, and a little maze, it's a little track. And they hear one of two sounds. One sound tells them if you go to the left, you're going to get food. Wheep. Go to the left, get food. Different sound, phew. Go to the right. So they learn this. You hear wheep, go over here, you get food, phew, go to the right. And then we let them go to sleep. And then while they're asleep, in non-REM sleep, about every 10 seconds or so, we just play one of those sounds. Wheep, phew. And just do this throughout the night. And then go back and look at the data and ask, when we play the left sound, what does the hippocampus do? And of course, you know the answer to this. You play the left sound, the hippocampus replays the memory of going to the left. You play the right sound, the hippocampus replays the memory of going to the right. When you look at the data, we were able to engineer these dream states to get the animal to dream of running in this maze a particular way. So the idea that perhaps we learn during sleep. Now, there's a lot of work showing if you disrupt sleep, it impairs learning. This experiment showing that you can selectively enhance performance. But how do we learn? Well, the way we normally learn while we're awake is we learn by reinforcement. We do things that lead to goals, that give us rewards. When we get rewards, we do those things more. It's like how you train your dog. You tell them to sit. If they sit, you give them a snack. They learn that the next time you tell them to sit, they'll get a snack. So you work for reward. In the brain, reward is signaled by a neurotransmitter known as dopamine. Dopamine is how the brain knows the things that we want to have. The brain loves to work for dopamine. And an interesting experiment was done by another colleague of mine, Karim Ben-Shanain in Paris. And in this experiment, what he did was to gain control over dopamine signaling by inserting an electrode and directly activating the cells that deliver dopamine. And by doing so, he could deliver reward artificially anytime he wanted. And if you put a rat into a box, let it wander around, and anytime it goes to one spot, you give it reward. You release dopamine. Rat will love that spot, and it'll go back to that spot. It will prefer that spot. It's called place preference learning. Well known, but now Karim did something very interesting. He let the animal go to sleep. And instead of triggering dopamine when an animal was at a location, he triggered dopamine when the place cell associated with that location went off during sleep. So whenever the animal dreamed about going to that spot, released dopamine. Now what he found was when he took the rat out now after sleep, put it in the box, guess what happened? You know what happened. The animal went to that spot that had been reinforced during sleep. It had never gotten rewarded for that while it was awake, only during sleep. This was remarkable. Animals learning something new during sleep. So we had to know, does this actually go on during sleep? Now, of course, hijacking the dopaminergic system, every drug of abuse works by hijacking the dopamine system. It will get you to do things that you otherwise would not or should not do. So we needed to know, does this really happen? And so we recorded from dopamine cells in the hippocampus when animals were running on tasks and sleeping. And what we found was when animals are sitting quietly, they're thinking, or you could say daydreaming, what we found is an animal thinking about running down a maze to get food. Indeed, when it thought about a goal location that had reward, dopamine cells fired. So animals would think about what they're going to do and think about the consequence or the reward. Then we looked during sleep. And what did we find? Indeed, the hippocampus replayed sequences running down the maze. When it would get to the goal, no dopamine, no reward. In fact, dopamine signaling was turned off. The brain was replaying memories, but it was trying to avoid reinforcing them. So you think, what? I thought the brain was learning during sleep. You can reinforce it, but you have to realize that reinforcement learning how to do things, is not the only kind of learning. There's another kind of learning, and that's learning about things. It's learning through exploration. It's the learning that comes from discovery, and that is finding hidden connections between things that you did not yet know. And it appears that it is this kind of learning that may be taking place during sleep. It is not learning and simply reinforcing that the things that we have done, but rather learning about the things that we might do. And that in the heart of dreams may lie the seeds of creativity, of insight. And that is learning about the world. And of course, this journey to understand what goes on during sleep is not over. We have a lot of work to do. But I think with a bit of effort, maybe with a little bit of sleep, and with a lot of help from our little friends, the rat, I think we will come to understand the connection between sleep, memory, and dreams. Thank you.